Okay, so today we're going to talk about analog to digital and digital to analog conversion. So in the first part of the course, we talked about analog electronics, which were continuous currents and voltages. And then we talked about digital electronics, which was ones and zeros and ons or off states. We restricted ourselves to a two-state system, and that helped us perform computational tasks. And often in experimental physics, what we want to do is we want to take sensor data from the real world, which is almost always analog, and we want to store that on a computer for analysis. And when we do that, we have two different types of data. We have analog data that needs to get converted into digital data. So we use a device which is almost self-explanatory in what it does, the analog to digital converter. On the other hand, we sometimes have digital devices which want to control voltages. Maybe it's a computer-controlled robotic arm, an actuator, or it's a direct digital synthesis audio frequency generator. So we have to do the inverse thing too. We have to get that digital data from the computer into the analog world, and that is a digital to analog converter. So let's start with analog to digital conversion. And we'll build this up before moving to digital to analog. So somehow we have to take our continuous voltages and turn them into bits. Now there's a number of different technologies that exist for analog to digital conversion, but we know how to build them. In fact, using the black boxes we've already understood in this course, we can completely understand what an ADC does or how to build one. So let's make a fairly simple one, a single slope ADC as it's called, and out of the stuff that we've already analyzed in the course. So we'll start with a few things we know: an integrator, a comparator, and a counter, a digital counter. So let's lay them out. So we first have our integrator with some RC time constant, and our input, our analog input, is going to go into the integrator. Now what we'll do is we'll wire that. This is going to be kind of a timing element, and we're going to wire that to a comparator that'll give us a yes or no. Okay, and we put that comparator, we wire the inverting, or the non-inverting, sorry, input, a negative reference voltage. And we're going to wire this in to start or stop our digital counter. And we'll see how this works in a second. So our third black box that we need is a digital counter. And in the counter, we're going to have a clock going into it. And we'll feed the comparator to enable it to work. Or rather to not enable it, so that when that input goes true, then we will stop counting. And this clock is going to keep counting and just count up 0, 0, 0, 0, 0, 1, 0, 1, 0, and so forth. And what this thing will do is it'll spit out our digital output. Okay, and this is going to be a simple analog to digital converter. So let's understand how it works. So if you recall from our integrator that if we have a constant input, which is, suppose for now we have a constant input, and it's going to integrate that constant, that will give us a slope, or rather a negative slope, because the output is the negative integral of a constant. So it's going to slope down, and the steepness of that slope is going to be proportional to the voltage input. So our integrator is going to look like this. That's what it looks like at the output of that integrator. And this is fed into our comparator, and eventually it's going to become lower than our negative reference voltage with this very illegible Vref here. Let's draw that as a dotted line. So at that point, the output here on the green line here is going to be going high. And then we'll stop counting and read out what we get. Okay, so this is how it works. Now if we had a steeper slope, we'd reach that faster. If we had a shallower slope, we'd reach that slower. Okay, so this gives us a voltage to time converter. Now you might notice that it's going the wrong way. The steeper slope will give us a shorter time, but we can fix that. But for now, let's just concentrate on the fact that we have a time, a number of cycles, which depends on the voltage, right? So during this time, we had a constant clock cycle. As it's going up and down and up and down, the counter is counting. So the output is going to do something like 0, 0, 0, 0, 0, 1, and so forth, until eventually, maybe it gets to 1, 0, 1, and that not enable goes high, the comparator gets tricked, or the comparator gets triggered, and it stops. So we read out that voltage now, 5 in this case, and we're done. So that gave us a digital output based on our input voltage. There's one problem here. What does 101 mean in voltage? Okay, well, we have to think about that. But basically, what we can do is we can calibrate it. We can put in a fixed voltage. We get 101 whenever we had 2.5 volts, say, and therefore we have 2.5 volts is equal to 5 bits, or half a volt per bit. So we'll go into that in a bit more detail, but we can always calibrate this because what the analog to digital converter is doing is it's just putting out numbers, zeros and ones, and we have to interpret that. We have to calibrate it ahead of time. But once we do that, we can now output that in terms of volts. Okay, so where does that leave us? Before I say anything else, there's a slightly more complicated design. It's not very complicated, in which we switch between an analog input and a negative reference voltage. And basically we're going to integrate down for a fixed time. We're going to switch to a negative voltage and it's going to integrate back up. And what that does, this so-called dual slope ADC, is it gets rid of a lot of the errors that we might have when the resistance or the capacitor changes. But that's just details. Right now we're just understanding the principle. So let's continue with this. So we have somehow 101 corresponded to 2.5 volts. And let's think about how the limitations are and what some of the key parameters are. So let's think about a plot of what we might get when we put in voltages of this type. So here's an example analog to digital converter with 3 bits of resolution. This is what a plot might look like. And we can start enumerating this. So here we see that we have 0, 0, 0 going to 0 volts, 0, 0, 1 going to, it looks like, about 0.5 volts. And let's understand where this comes from. So here's an example plot of such a digital to analog converter, an analog to digital converter. It's a 3-bit ADC, and we can see a few key points here. We had an input voltage, which is some varying wave here, and the output that we're going to get at an ADC. Notice that there's a few key characteristics here. There's the step size, there's the resolution, which is basically the number of bits. So the bit depth, or resolution, sometimes also called the resolution, but we'll keep it at the bit depth, is just the number of bits. And typically the more the merrier, is we have higher bit depth. If we had 8 bits, we had 256 possible values here, and this curve would look a lot smoother. So that's one thing. We'll say AKA resolution. Another thing of interest is the range of voltages. What values of voltages will give us an accurate measurement here. So here it looks like we have a 0 to 3.5 volt range. And the range is a bit of a thorny issue with the ADC, because you can argue that the range is up to 4 volts because it gives you the correct value up to 4 volts. You wouldn't have gotten anything from having a higher bit depth, but this is typically the way it says. It's a range of possible values. And here it's 0 to 3.5 volts. When we combine the resolution and the range, we get the precision. That is the step size. What is the minimum voltage that we can differentiate? And we can just plug that in as follows, which is the maximum voltage minus the minimum voltage over the maximum bit minus the minimum bit. So here, let's see what that is. That's going to be 3.5 volts divided by 111, which is 7, minus 0. So that's going to give us 0.5 volts per bit. Okay, so we get 2 bits per volt, another way of putting it. And this is an important characteristic. This tells us that we won't be able to tell the difference between 0.2 and 0.3 volts. And it's going to give us kind of one part of the accuracy of our analog to digital conversion. So the accuracy that's related to the precision, certainly I should say that the precision causes a loss of accuracy in that we have a loss of information. This range here is what we call digitization error. But we also have the other things which will affect the accuracy, which can be affected by things like linearity, which means that each step is the same height, basically. That going from 0, 0, 0 to 0, 0, 1 gives me the same voltage as going from 0, 1, 1 to 1, 0, 0. Okay? And there's other things, there's other kinds of distortion. You can even have what's called non-monotonicity, which is a form of linearity when it's so nonlinear that if you increase it, if you're increasing the voltage, the bit will actually go down. And this is bad. So there's other ways of quantifying the accuracy of this thing. But the bottom line is you want it to be linear, and the number of bits you have determines your resolution and your accuracy, how accurately you can measure 2 volts. And you can build one this way. There's a number of different ways to do it as well, but we won't go into all the different technologies. So just as a quick numerical example, let's say we have a 1.2 volt 2-bit resolution ADC. 1.2 minus 0, so 1.2 volts divided by 2 to the 2 minus 1. So what's the maximum bit I'm going to have is 1, 1. I can also write this as 2 to the n minus 1. I should actually write this over here. Delta V over 2 to the n all minus 1. That's the maximum minus the minimum bit you're going to get. Okay, so in this case, this is 3. So this is going to give us 1.2, so 1200 millivolts divided by 3, which is 400 or 400 millivolts or 0.4 volts. So we've got 0.4 volts is our resolution in this case. And let's look at the possible voltages that we can measure. If we have 0 volts, let's just say it's really a range. So we say V is between 0 and 0.4. We're going to get 0, 0, 0. Again, there's a bit of an ambiguity. If V is negative 200 volts, we're probably going to get 0, 0, 0 as well, but that's not guaranteed. So if we're on 0.4 to 0.8, I gave one too many bits there, we're going to get 0, 1, 0.8 to 1.2, and I better be a proper mathematician and close these brackets properly. Anything up to but not including that, I'm going to get 1, 0. And then I'm going to say V greater than 1.2 volts, I'll get 1, 1. So you could argue again that the full range of this thing is actually 1.6 versus 1.2 volts. But the key point is the step size. What is a step size? So you have to be careful to read the spec sheet of your ADC or whatever, whenever you're buying it, to find out what the designers mean when they say, I have a 1.2 volt V reference ADC. Okay, there's one other thing that we didn't talk about yet, which is the x-axis here, the horizontal axis, time. So it turns out we get some very interesting problems that can creep up when we have a fast signal that we're sampling too slow. This whole sampling theory is a big topic, so we're going to leave that to a separate lecture. It's going to be covered in class. So let's move now to digital to analog converters, or DACs. So a DAC poses the opposite problem as the ADC. We will have a digital stored number somewhere. We want to convert that to a real world voltage. We have to do that somehow. And it has the same kind of parameters of interest, resolution, range, accuracy, linearity, as our ADCs. But the construction is a bit different, and the task is opposite. So let's have a look at a graph that we might get from a digital to analog converter. Now DACs have the same kind of specs that we were worried about as ADCs, resolution, range, accuracy, but now the precision is more well defined. There's no 1.2 versus 1.6. It's really the step size, the difference between the voltage that I get if I command 000 versus 001. So for example, let's look at an example here. If I have a 10-bit 5-volt DAC, first of all, what's the resolution? Well, we have 10 possible bits. And let's look at this for the example of a 2-bit just for a second, because this is an interesting counting problem. This would be 00, 01, 1011. So these are the possible values you can reach. Really, this defines 2 to the 2 minus 1 possible slots. This is known as a fence post counting problem. If you have n fence posts, how many fence panels do you need? Well, you need one fence post on each side, and there's this extra one on one side. So you have post panel, post panel. You need a post for the last one. So if you have n posts, you need n minus 1 panels. And this is one of these counting problems that comes up all the time. So we have 4 distinct values we can command with a 2-bit digital to analog converter, but that's only 3 ranges. Okay, so that's the confusing part here. So again, we're going to look at what the output is here. Let's have a look. So we're going to have step sizes given by the total voltage range divided by 2 to the n minus 1. So 2 to the 10 is 1024. So it's going to be 1023 in the denominator. And so we can just calculate what that is. Let's calculate it. So when I do that, I get 4.89 millivolts per bit. Okay, probably more accurately than we can command because of noise and stuff, but let's hang on to it for now. So that means, let's look at the possible values we're going to command. Okay, so as I start counting this thing up and outputting 10 zeros, I'll get 0 volts. If I output 9 zeros followed by 1, I'll get 4.89 millivolts. Again, probably won't get this voltage resolution because there's going to be other noise in the system, but this is what it's ideally putting out. And we can put out 2, which will give us twice that value, which is 0.00, which will give us 0.00978. And then we can just count up our 2 to the 10 or 1024 possible values as we count this up. Before we get to the penultimate, whoops, and I put millivolt when I should have put volt up here, and the final voltage value. So this can command a lot of values. That's a lot of precision. That'll be it'd be very difficult to tell any digitization error, although it would be there. So there's a few other considerations that we have to worry about. We have to worry about clipping on the range and the resolution as before. So let's have a look at a graph that we might get from one of these. Okay, so as before, we have a desired output. And what we're going to do is we're just going to set the digital to analog converter to those points. And it's going to fairly quickly jump to those values. But you see you get a squarish wave here. And the higher the bit depth, the more resolution you're going to get. So it'll be a closer approximation. But there's going to be clipping problems from below and above. So you're never going to be able to command anything below there or above here. And in between, we're just going to keep at the same value. Now there are fancier things you can do in between points. You can try to interpolate them with a predictive method that's called first order hold. But you can also have zero order hold, which is just saying keep it constant between points, and that's what most of them do. You can also smooth out things with a capacitor to get rid of some of the kinks. Okay, so this is a 3-bit digital to analog converter with the same delta V that we had before. It looks like delta V in this case is 1 volt. Okay, and I just noticed there's an error in my Python programming. I made it a 9 value, so not quite a 3-bit digital to analog. So if it was actually 3-bit, we'd actually clip off here. So there is also the rate at which you put up points, and that is the speed of the digital to analog converter. And that's set by your clock. It's also important for accuracy. Okay, so to wrap this up, let's make a physical implementation of one of these. Common usage is the so-called R2R ladder. Let's have a look at that. Okay, so here's what's called an R2R ladder. Now this is an n-bit R2R ladder, so there might be 16 of these things or 24 of these things. And what we do is we just have this common pattern of a 2R resistor and an R resistor. So there's a few things to note about this. So the output impedance of this thing is just R, no matter how many stages you have, no matter how many N you have. Here, each one of these BN or B1 or B2, they are bits that can be set either to high, 5 volts say, or 0. So they can be switched digitally as either on or off. And if they're off, they're grounded. If they're on, they're at high, so 5 volts say. And the output voltage is as follows. Okay, where Vref is whatever 5 volts or 3.3 volts you choose for high. And we have exactly as we want. This is a binary addition. So for example, for a 4-bit, we'd have an output like this. Times 5 volts say, or 2 volts say to make the numbers nice. So this is exactly what we'd get, what we'd expect to get for binary addition, right? Each bit is worth a factor of 2 more than the one that goes before it. So this is an implementation of a ladder digital to analog converter. And you can prove this without too much trouble, maybe a bit of trouble, but not too much. It's a fun exercise in Thevenin equivalence. Okay, so what you do is you take these 2 points, say you have some giant load resistor, some fictitious load, and you find the Thevenin equivalent circuit using everything to the right of that as the load. So you're going to get something that looks like this. Vthev R is the output impedance times the rest of the ladder. Dot, dot, dot. And then what you do is you find the Thevenin equivalent of the next part, and you can kind of collapse it down. And what you get is an expression that looks like this. It's a bit much algebraically for a lecture, so let's just look, kind of convince ourselves that it's true for a 2-bit, and we can go from there. You can always prove it or let me know if you want. We can go through the full derivation if you want. It's not too bad, it's just a bit much. So let's look at a 2-bit digital to analog converter with some R. I don't even know what it is. We don't even have to specify it, so that'll look like this. We have B0, B1, and B1, and that's our output. Now let's talk about the output very briefly. Typically we're going to put an op-amp there. So we have kind of an ideal source. There's 2 approaches. We can put an inverting op-amp, something that looks like that, and therefore this is kind of a current source. Our outputs are negative though, or we can put just a simple voltage follower, which I prefer, and this is exactly what you do in the lab, because you get positive voltages if you have a single supply rail. You can do tricks with the inverting one, like set a virtual ground at halfway through the maximum reference voltage and stuff, but I think this is most straightforward. So we're just going to put a infinite resistor, say, a buffer op-amp, an ideal load at the end of this thing. All that is to say is that we don't really need to worry about what happens here in this analysis, because it's going to be like an op-amp or something like that that draws no current. Okay, so let's make sure that everything makes sense. Suppose first of all we put 0, 0. So B0 and B1 are ground. Well, if we just look at our circuit now, there's ground everywhere. We're going to get these 2 things are tied together to ground. We have a resistor here. Don't even need to know what the value of the resistor is. That's ground. There's no voltage sources. So there's no way this thing is not 0 volts here. So 0, 0 kind of almost trivially goes to 0 volts because there's just nothing plugged in anywhere. We're always going to get 0 volts with respect to ground at the output because all our inputs are ground. Okay, so that works. Let's look at a slightly more complicated case. Let's look at 0, 1, for example. 0, 1, and what does that look like? Well, B1 is set to ground, and B0 is set to 5 volts, say, or just we'll call it V. So we have V, and B1 is ground, so that just goes right down to ground here, like this, right? Because B1 here is actually just ground. So in this case, we can rewrite this using our circuit analysis that we might have used before, and it's 5 volts, of course, with respect to ground. So this is going to give us a circuit that looks like this. Surprise, surprise, in this course, we're going to get a voltage divider. So we get 2R and an equivalent network that looks like a parallel combination of 2R and 3R. Okay, so that's what the circuit looks like here. Our output is kind of halfway through there, but just bear with me here. We'll get there. So let's find out, first of all, what the voltage across here is. What is that voltage? Well, this is a parallel network of a 2 and a 3, so that's going to be 3R times 2R over 2R plus 3R, so 6/5 R. And that's our voltage divider, that's our R2 in our voltage divider. So delta V is going to be equal to what? R2, which is 6/5 R, divided by 2R, which I'm going to call 10/5 R, plus our 6/5 R. Why? Because I'm incredibly lazy and I don't like fractions. So it's 16/5 R. The R's are all going to cancel out. And oops, we can't forget our V in here. So we're gonna get 6 over 16, 6 over 16, or 3/8. Man, this is a lot of work. This is why we just do the Thevenin way and solve it generally first. But we got a voltage drop across this 3R network of 3/8. So let's look at the current here. So the current here is just V over R, right? So the current is I is equal to V over R, which is, let's write it out, V over R total. And that's equal to 3/8 V in divided by R total, which is 3R, almost there. 3's are going to cancel. So we're going to get V in over 8R. That's my current through this node here. Finally, our output voltage right here is going to be IR from Ohm's law. So V out is equal to I times R, which is equal to V in over 8R times 2R, which is equal to V in over, okay? Whew. That was a lot of work. We can do the same kind of analysis for setting both of these high in the same way, or we can set one of them high and the other one low. Let's just do that really quickly because that one's going to be a bit easier. So if we set this one, for example, to 0, 1, that should be 2, 1, 0. We're going to get 5 volts here, and that goes directly to 2R resistor. And then what happens? It hits a output here, and that goes to a resistor here. And then since B0 is at ground, we're just going to get a combination of 2R and 2R, which is going to give us an R. And this whole thing will give us 2R. I know I'm just in the wild, wild west here, driving things crazily, sorry. But this is going to be a voltage divider between 2R and 2R. So this is going to give us V in, our 5 volts divided by 2, or 2 times our input voltage of V in over, our resolution of V in over 4. So we got 0, a quarter, a half, 2 quarters. I'll leave it to you to prove that when they're set to 5, they're both set to 1, 1, you'll get 3 quarters. But this is kind of a way to analyze one of these things. It's just an exercise using other stuff in the course. So the key points here for both analog to digital, the key points is that we have resolution, which tells us our number of bits. We have a range that we need to worry about, and we have a precision, which relates the two. The more bits, the more precise you have. Okay, that's analog to digital and digital to analog conversion. And that is it for this lecture. In the in-class lecture, we'll talk about what happens when you worry about sampling and what rate you're actually sampling at. And this will wrap it up for the DC part of the course.